was gonna prank call you guys and tell you that I got a bunch of tattoos, but I don't think anyone would believe me. All right. Okay. Anyone else need the guided notes from yesterday? Okay. So we did a lot yesterday. We talked about a lot of different types of derivatives. I introduced a lot of them to you. A lot of them involved trig, right? So a lot of stuff you had to memorize before the quiz today. We derived some of these. So we derived the derivative of sine, which was cosine. We also derived the formula for the derivative of tangent, which was secant squared. And we talked about how you could use the quotient rule to get that. Okay. And we also had all these trig derivatives that I told you you had to memorize for the quiz tomorrow. So make sure you know these in your head. Okay. And they'll help us throughout the class a little bit later. Okay. We were able to kind of piece together these trig derivatives to find derivatives of like quotients and products of trig functions. And I think let's start with talking about how to use the chain rule for trig derivatives. Okay. So looking at this function here, we have the sine of 4 theta squared plus 3. How do I know that this is a chain rule question?
There's a parabola inside that sine, so it can derive from.
Yeah, like there's an inside function, which is the parabola, and then there's an outside function, which is sine, right? So because we have a function on the inside and a function on the outside, this is an example of chain rule, okay? So chain rule, okay? What's the inside function? Oh, thanks. 4 theta squared plus 3. Okay. And I promise I'm not muted. It just says that I'm muted up there. What's the outside function? Sine, right? Sine is being applied to the inside function. It's on the outside. Now, I like using little boxes because in my head, it's easy to think about filling in the box. So this is the outside function. Okay. Remember, chain rule is the derivative of the outside function times the derivative of the inside function, right? So what's the derivative of my outside function sine, Michael?
Cosine.
Yeah, cosine of the big blob. Okay. And we're going to multiply that by the derivative of the inside, which is not 0. Oh, it does involve a 0, but 8 theta plus 0, right? Oh, sorry. Yeah, it does look like a 0. It's actually a theta. Sorry about that. I was like, why are you saying 0? Yeah, this weird circle with a line in the middle, that's the Greek letter for theta. Okay. So we can clean this up. First of all, I can write the inside function in my little blob. We have 4 theta squared plus 3. Okay. And I can take away the 0 because 0 is just itself. So 8 theta cosine 4 theta squared plus 3. Okay. So chain rule just works like any other function or any other rule that we have. It doesn't matter that we have trig functions. It works exactly the same. Okay. Any questions before we start putting everything together? All right. As we go on with this class, we're going to see a lot of different derivatives. David? Oh, okay. Here you go. Okay, you're welcome. Okay, as we go on, we're going to see a lot of different types of derivatives, and we're going to see a lot of different functions. Now, what I want to do is kind of consolidate all our derivatives into one place so that you're going to be able to go back and actually find these later on if you're ever confused and want to look up the derivative. Now, so on this chart, I have a bunch of different functions on the left. Some of them you haven't seen before, but as you can see, I did leave off polynomials because I think we've been working with those a lot. So you actually do know a lot more derivatives than just the functions on this list. But I did want a single place where we can look at all these derivatives and kind of abstractly find what these actually mean, okay? So on the top, I have these different columns. One of them is going to be just the derivative. And on the right, we're going to have the chain rule. So as we look at the chain rule, what are our derivatives going to look like? Okay. So first one is probably our easiest one. We have e to the x. Everyone at once, what's the derivative of e to the x? 3, 2, 1. Good, e to the x. Good. Okay. And let's see what e to the x looks like as we apply the chain rule to it, but maybe not with a function, okay? So let's just say there wasn't an x in the exponent, like it's a different function. I threw a lot of them at you before, and I wanted to find the derivative of e to not x, but a function of x, like f of x. Okay, so maybe e to the x squared or e to the 3x, something like that, okay? Using the chain rule, and I know we've done this in steps before, I would know that my inside function is the f function and my outside function is the e function, right? Can someone tell me what the derivative of the outside function is? Like e to the f of x, or our inside function. So e to the f of x, very good. Okay. We're going to multiply that by the derivative of the inside function, which is what that? Yeah, the derivative f of x or f prime of x. Good. Okay. So normally, just for notation's sake, I'm going to put the derivative of the inside first, just because it looks a little bit nicer. But in general, when we're applying the chain rule, we're going to multiply our derivative of the inside, keeping derivative of the outside, keeping the inside alone, times the derivative of the inside. Okay. Any questions so far? Okay. Next of all, we have a to the x, which is basically e to the x, but a little bit more general. Does anyone remember the derivative of a to the x?
Natural log a times a to the x.
Natural log of a times a to the x. Good. Now, natural log of a isn't a function of x at all. It's just a number, right? So ln of a is the same as 2 or 4 or 6 or pi or something like that. Okay. So just to keep in mind of that. Okay. Putting the chain rule in mind. Let's say I didn't have a to the x, but instead a of a function of x. So a with something else other than x up top. Okay. What would the derivative of the outside be?
Natural log a times a to f x times f prime of x.
Good. So you went a little bit further, but the derivative of the outside would be this. Keep it doing the outside function, but leaving the inside alone. And then, as Jude said, the derivative of the inside function is still f prime of x. Okay. So as we went from e to the x to a to the x, our function or our chain rule derivative changed just by a factor, right? Just changed by ln of a. Okay. Are we all good on e to the x and a to the x? Good. Let's go down to sine of x. Derivative of sine is cosine, good. And we can apply the chain rule in the same way, right? We can do the derivative of sine, but instead of x in the middle, we can write f of x. So very similar to what we did in the last problem, okay? Now we have an inside function and the outside function is sine. What do you think the chain rule derivative is going to be? Ooh, you're really close.
F prime of x cosine.
Seeing a lot of things. Cosine of not f prime, but f of x, right? Cosine keeping the inside alone, and what are we multiplying it by? F prime of x. We had a lot of words going on there, but we eventually got there, right? Okay, so we're taking the derivative of the outside, leaving the inside alone, and multiplying it by the derivative of the inside. Okay, any questions here? Good. Okay, oh, what? Oh, sorry. let's do some quiz review here. What's the derivative of cosine? Negative sign, good. And if I were to take the derivative of cosine of f of x, what would be the derivative? Negative sine f of x, right? And I would multiply it by its derivative f prime of x. To make things a little bit neater, I'm going to take the negative out up front and multiply it over. So it's negative f prime times sine of the inside. Okay. Okay, quiz review. What's the derivative of tangent? Not secant tangent, that's the derivative of secant. Secant squared, good. Remember, tangent and cotangent have the squared derivatives, okay? Okay. The derivative of tangent of f of x is what value? What would the derivative of the outside be? Sec squared of f of x, right? No, you're good. And what would I multiply it by? The derivative of f of x, good. So the chain rule works very similar no matter what function we're doing. Okay. Okay, cosecant x, what's that derivative? Awesome. Negative cosecant, oh my gosh, cosecant x, cotangent x. Okay. Now this chain rule is going to be a little bit different because we have two x's in our derivative. Let's see if we can figure this out. So I want to find the derivative of, gosh, cosecant of f of x. What would this derivative be? What's the derivative of the outside? Cosecant f of x. Okay, there's a negative. Cotangent of not just x, but actually just f of x, right? So the derivative of the outside, and I did put the negative there up front, is just the derivative of the outside function, but we leave the inside alone. So we're not touching that inside function. That's why we just have f of x in the middle and not f prime. Okay, so we're not dealing with f, the derivative of f yet. Once we're done taking the derivative of the outside function, we can take the derivative of the inside function and multiply that over. Let's see if I can do this. F prime of x. So this derivative is negative. The derivative of the inside times cosecant of the inside times cotangent of the inside. Okay. Any questions so far? I think we're doing good. Secant is very similar. What's the derivative of secant? Secant x, tangent x. Okay, let's do the derivative of secant of f of x. Okay, what do you think that derivative is going to look like? What's the derivative of the outside?
Secant f of x, tangent f of x.
Perfect, secant f of x, tangent f of x. Okay, and we have to multiply it by the derivative of the inside, which is f prime of x. So as we can see, the chain rule gets really kind of repetitive as we work with these trig functions. Okay, cotangent of x, what's that derivative? Squared, good. Remember, tangent and cotangent have those squared values. All right, let's find this derivative of cotangent of x. Okay, any guesses on what the whole derivative would be?
F prime of x
Mhm.
times cosecant squared f of x.
Perfect. And that's all we have to do. Very good. Any questions on these trig functions? Okay, now I come up with this chart and I don't want you to memorize everything on the right-hand side. I think that would be a little bit scary, but I do think it's a good exercise to go through and do this in the abstract, because then it's easier to do it in your head when you are doing actual functions. Let's go on to two derivatives that we haven't seen yet, okay? The natural log of x. We haven't talked about the derivative of this, and it's kind of, it's 1 over x, good, yay. It's actually, it's kind of on my fault that I haven't told you about this. I meant to put this in a note packet before and I just forgot. But yes, the derivative of the natural log is 1 over x, okay? What is the natural log? What's another way to describe the natural log?
Like the log base form.
Not one, log base E, good. It's actually log base E of X. So E is kind of like derived from our natural logarithmic function. Okay, so let's do a little chain rule question, okay? Let's do the derivative of the natural log of a function. Okay. My inside function is still f of x. The outside function is the natural log. What do you think the derivative of the outside is going to look like?
Can you see x minus 1? Oh,
Not quite. We're not using the chain rule on the derivative. That would be the second derivative, but it'd actually be 1 over our inside function. Right, so we take the inside and we just stick it in the derivative. So instead of x, there's f of x. Does that make sense? I think you're talking about the second derivative, which would be fine, but the first derivative would be 1 over f of x, okay? And we have to multiply that by the derivative of the inside, right? So I know if you write this down, I'm very sorry, but another way to kind of clean this up is to stick the derivative on the inside on the top, right? So it's actually f prime of x over f of x. Okay. Any questions so far? Okay, so the chain rule says take the derivative. Let me, I'm going to do this. You don't have to write this down because I'm going to erase it later. Okay. This is, for example, let me just do a little example here. And you don't have to write this on your chart because I'm going to erase this. Let's do the natural log of 2x. Okay. Now the inside function or f of x is 2x, right? So the inside is 2x. The outside function is the natural log of something, right? So if I'm doing the chain rule and I want to do the natural log or the derivative of the outside, what's the derivative of ln? 1 over x, but instead of x, we have a box, right? So that's why we have f of x on the bottom. Okay. Now on the top, we have the derivative of the inside, right? We want to multiply by the derivative of 2x. And what's the derivative of 2x? 2, good. Okay, now instead of writing the box, we can write our function. Okay, so this is my function. 2 is f prime, and that's why f prime is on top and the derivative of the outside leaving the inside alone is on the bottom. Yeah. Any questions so far? Okay, I think I think this one's a little bit hard to see in the abstract. I won't require you to memorize the chain rule, but it is good to think of it about like what happens in general. Okay. Now the last one is a little bit sneaky. Okay. And before I even find the derivative of, or tell you what the derivative of log a is, we're actually going to try to change our function very similar to how we changed, oh, we didn't actually change anything. Of how we would change like 1 over x to a negative exponent to find the derivative of log base a. Okay. I don't know the derivative of log base a of x, but there is a way to change it, change the function into something involving the natural log. Does anyone know how to change it?
Can you see it's over x and spell out a natural log of a?
Very close, but it's actually a different factor, and there's a reason why. Does the change of basis formula ring a bell to anyone? Yeah, I actually normally don't even teach this to my pre-calc class at all, but there is this thing called a change of base formula. Whenever we have log base a of x, we can always change that. So this is the same function as, I can choose whatever base that I want, okay? And turn my base into the denominator, okay? And since I know the derivative of ln, maybe I want to change my base to log e. And that looks really nasty, so log e. Okay, so another way of saying log base a of x is saying log base e of x, over log base E of A. Okay. Okay, what's log base E of X? That's another way to say it. ln. Oh, no, well, that's the derivative, but this is ln of X, right? And log base E of A is ln of A. So technically this function is 1 over ln A times ln X. Okay. What's the derivative of 1 over ln A times ln X?
One squared by 1 over x over 1. The
Not
product.
quite. Is this a function? Hmm. Now, you did say product rule, which would work with a constant, but what is 1 over ln A? It's just a number, right? 1 over ln A is like 2 or pi or -5. This is a constant. Okay. So 1 over ln A is just something that I'm multiplying ln X by. What do you think the derivative of ln log AX is now?
0.
Not 0.
1 over ln A times X.
Close. So I'm going to take my factor.
Oh, I meant X on the bottom.
Oh,
ln A, sorry.
oh. Yes, times 1 over X, which is, let me write it how John said it. 1 over ln A times X.
That's what I said.
Oh, is that what you, I'm sorry. I'm so sorry. Yeah. Okay, this is what it would be. For some reason in my brain, I was thinking about 2 fractions. My mistake. Okay, now let's find the chain rule. Let's do the derivative of log A. I did that wrong. Log A of f of X. What do you think the derivative, and you can kind of compare it to the row up top. What do you think this derivative is going to be?
Prime X over ln A times f of X.
Perfect. It's basically this derivative, but offset by a factor of ln A. Okay, so it's literally multiplying the derivative by this constant value. Okay. Any questions on what I've done so far? Okay. Now, I do recommend that you have this on hand. You don't actually need to memorize the chain rule derivatives. I think that would be a little bit asking you a little bit too much. You really only have to know these, but knowing the chain rule column, or at least how to get there, is a useful thing to do, especially when you're learning how to take these derivatives. Now, some of you might get a little mad at me, because in a sense, you actually didn't have to write this down. Yeah. Does anyone know where to find this chart? Or okay, yeah, it's on the back. It's also in your textbook. So this whole chart is in your textbook. If you go to the index page, there's a huge chart that tells you all the derivatives of everything and even what the chain rule looks like. And it looks like this. It's not from the textbook, but it looks something like this. Don't worry about these guys. We won't learn about those yet. But the reason I had you write this out, I like creating charts and writing things out by hand. And I watched this video of this guy who kind of explained why he liked to make these charts. And I thought it was kind of illuminating. He said when he was in school, there was a guy named Johnny, and he did really, really well on all his tests. So he got like perfect hundreds on every single test that he did. And he made these beautiful charts that he wrote by hand that kind of look like the page before, probably a little bit neater. And the thing about Johnny is he was really generous. So he, if anyone asked him for his charts, he would give the charts to them and they would have these beautiful notes. But for some reason, even though the people had all Johnny's notes, Johnny still did better than everyone he gave the notes to. Does anyone know why?
Because you were, you are understanding.
Yeah, he wrote it in the way that he understood it, right? So he took the information, he organized it in a way that made sense to him, and he wrote out his own page of notes, right? So what I recommend you to do is to do something like this. It doesn't have to be like this. I want you to organize your information in a way that makes sense to you. Maybe it uses colors, maybe it's a different type of chart, but do something that makes sense in your brain And I think it will be very helpful for you to memorize these derivatives instead of just looking at my notes or looking at the textbook. Of course, the textbook is a good reference, but I do recommend making your own charts when you do calculus. Okay. Any questions before we move on? All right, let's go to example number 4. Okay. Yeah, I think we have. So this example is telling us to find the derivative, and this just means take the derivative of with respect to n, since n is our variable here, of tangent of cosine of n. Okay, so now we have a crazy thing. We have 2 trig derivatives. Anyone know what rule we're using here? Chain rule, because looks like we have something on the inside and something on the outside. Okay, so inside function. What is on the inside? Cosine. And what's on the outside? Tangent. So I know a lot of people use U, which is fine. I like using the big box because I can like write stuff in the box. Okay, what's the derivative of tangent? Secant squared of my box, right? And I'm going to multiply that by the derivative of the inside, which is, so the derivative of cosine is, oh, you're saying the derivative, the inside is cosine? What's the derivative of cosine? Ooh, negative sign, right? Sine of n. Okay. You don't have to put the parentheses, but for some reason, I'm definitely going to forget to write 2 n's. So I'm going to put a parentheses there. Okay, looks like we can write the inside in the box. So cosine n. Okay, and finally, our answer is secant squared of cosine n times negative, I'm gonna put the negative on the outside, sine n. Okay. Maybe I should put brackets around this just to separate this if I look at this again. You don't have to, but I would recommend doing it. Any questions on example 4? All right, how about this? Why don't we work on example 5 and 6? I don't know if we're going to get to example 6 today, but work on these 2, and we'll come back in a little bit. You know, as I was walking around the room, I realized that the board kind of looks like a Dunkin' Donuts ad. I don't know if you've seen the colors on Dunkin' Donuts, but it kind of does look like Dunkin' Donuts. All right. Let's go through example 5. We're finding the cosecant of the natural log of a. Michael wrote up his answer. Do you kind of want to take us through your process here?
The derivative of cosecant is cosecant x cotangent x, or negative cosecant x cotangent x. So you have to plug in the inside function, and then you multiply by the derivative of the inside function. And then when you put it all together, you just put it all over A, so multiply it.
Great job. Any questions on example 5? All right. Well, I think it's about time to take our quiz, right?